Cardiac conduction velocity is the velocity at which a depolarization wave moves through the myocardium, which is the muscular middle layer of the heart, and it's measured in meters per second. Now, the depolarization wave travels through the sinoatrial node, or SA node, both atria, down the atrioventricular, or AV node, through the bundle of His and the Purkinje fibers, and finally to all the parts of the ventricles, all in about 220 milliseconds, which is less than a quarter of a second. If we zoom in on the myocardium, the depolarization waves move across neighboring cells. It moves from one cell to the next when ions like calcium and sodium slip through gap junctions and trigger voltage-gated sodium channels in the adjacent cell to open up, allowing a rush of sodium into the cell and causing an action potential to happen. That then results in more sodium and calcium leaking through to the next cell, again triggering an action potential, which goes on to the next and so on. Ultimately, these cellular processes determine how fast or slow a depolarization wave will move across different types of tissue. More sodium channels and gap junctions speed up the depolarization wave, and fewer gap junctions and sodium channels slow down the depolarization wave. Alright, so let's break down the conduction velocities in the different parts of the heart. Starting at the SA node, the depolarization wave moves through the myocytes in the atria at about 1 meter per second. Then goes through the AV node super slowly, at about 0.01 to 0.05 meters per second. Which means that even though this is a super short segment, it takes a relatively long time. In fact, out of the 220 milliseconds for the entire journey of the depolarization wave, about 100 milliseconds, or almost half the time, is spent in the AV node. That dramatic slowdown lets the atria contract and push blood into the ventricles while the ventricles are still relaxed. After that, the conduction velocity in the bundle of His and Purkinje fibers of the ventricles goes back up to 2 to 4 meters per second, which is the fastest in the heart. That allows the ventricles to contract all at once in a really coordinated way, so that the blood gets pushed out rather than sloshing from one part of the ventricle to the other. The depolarization wave therefore starts at roughly the same time throughout the ventricles, and then goes a little bit slower, about 1 meter per second, through the ventricular myocytes. Alright, as a quick recap, the conduction velocity of depolarization waves in the heart depends on things like the gap junctions between adjacent cells, as well as the voltage-gated sodium channels on the cells. The total time it takes for a depolarization wave to move through the heart is about 220 milliseconds. Through the AV node, it goes just 0.01 to 0.05 meters per second, making it the slowest bit in the heart, which gives the atria time to contract. But through the bundle of His and Purkinje fibers, it moves at about 2 to 4 meters per second, making it the fastest stretch and allowing the ventricles to beat in a coordinated way.